Today I'm going to talk about our work on understanding a class of very simple spectral methods for high-dimensional inference. And the type of inference problem that we consider, let's see if we, yeah. All right, the type of inference problem that we consider can be formulated like this. So we have some input or explanatory variables A that are n-dimensional vectors and some output variable Y that are scalars, and given a collection of these input and output pairs, we want to learn a function mapping A, the input, to Y. Okay. Of course, to make this type of problem tractable in a high-dimensional case, typically it is useful to make some further assumptions on the structure of F. And in this talk, I'm going to assume that Y is going to be a function like this. And essentially what we're saying is the output depends on the input A through its projection onto a low-dimensional subspace. And here, psi 1 to psi r is a set of basis vectors for this subspace, and G is some unknown functions that can be nonlinear and stochastic. And the geometry of this model is also very clear. Instead of trying to learn a function that depends on general n variables, we want to, we're essentially doing a nonlinear dimension reduction. And by doing so, we only need to learn a low-rank subspace and a much simpler function that depends on a smaller set of variables. Of course, this model is very general, so it is helpful to consider a few concrete examples. The first example is a rank 1 case. This is, of course, the classical generalized linear model that Lenka and a few others also spoke about in their talks. And here, learning this one rank 1 subspace is equivalent to learning this unknown vector psi. And you can think about this as a one-layer perceptron with a general nonlinear activation function modeled by a conditional distribution, right? Of course, the exact form of this nonlinear activation function comes from specific examples that we consider in different applications. For example, in nonlinear signal reconstruction, imaging, and binary data classification. Okay, that will give us different forms of this nonlinear activation function. And in this talk, we're going to use a particular form of this nonlinear function as a running example. This problem is so-called phase retrieval that comes from X-ray crystallography. The formulation is very, very simple. We want to estimate a vector psi. In the case of imaging, psi represents an underlying image we want to reconstruct. And we measure psi through its inner product with a collection of vectors, input vectors. And what we actually measure are the squared version of these scalar products. So we are missing the sign information, or in a complex value case, we're missing the phase information. That's why the problem is called phase retrieval. And there are other problems with similar mathematical structures. So for example, blind deconvolution, channel estimation, and so on. So last year, there is an interesting work generalizing the phase retrieval setup to the multi-rank case. And in that setup, the measurements yi is a linear combination of the phaseless measurements that correspond to r different images. So this is a mixture setup, and from these measurements, we want to decouple these measurement model, and we want to estimate these psi up to unknown phase and sign. Of course, this is a special case of the rank R case of the model that we consider, and there are other instances where this model appears in covariance sketching and so on. And another example of learning the rank R model is, of course, the two-layer neural network. So in this case, the psi's can be used to model the weight vectors in the first layer, and the coefficients and the nonlinearities in the second layer can be captured by our function G. Okay, it's a simpler function. I want to remark that inherently what we're assuming is that the input dimension is high and the rank R of the substrate is low. So this model only captures a very narrow model instead of a wide neural network. So the number of variables in the hidden layer in this case is small. So for example, like a committee machine type of model. Okay. Yes.
Go back to the phase retrieval.
Yes.
Yeah. So for given data A and Y, these are the data that you have. Right?
That's right, yes.
So it's invariant to the sign of psi.
That's right. So in general, it's invariant to the phase. So so that means the reconstruction is up to the unknown phase.
Right. So there is no phase retrieval.
Oh no, but in general, phase is about the phase of. So in this case, it's a phase of each entry. But what we're saying is you can reconstruct the phase up to a common global phase shift. Yeah. All right. Okay. So. Next, I want to very briefly mention a few other examples in the literature where this type of a general rank R case appeared. For example, in this work by Andrea and his collaborators, there is a linear learning dictionary mixture of classifiers. If you think about this, is a special case of a rank R model. And there are other cases, for example, phases PCA and the so-called max affine regression. So the point I want to mention this work is just to motivate you that this potentially can be an interesting model to study, but there are also a few challenges associated with the learning of this model. So what are the challenges? So here is our model. We want to estimate the subspace spanned by Kasai 1 to Kasai R and a general function G. Okay, and even in the case where G is known, typically estimating these subspaces boil down to a non-convex optimization problem. For example, if you are talking about phase retrieval, this is a nonlinear least square, and this is a convex problem. The actual challenge is when G is also unknown. Typically, the solution is to do some sort of alternating minimization. You first assume a form of G, and then you solve this type of optimization problem, and you iterate, right? Of course, as we all know, analyzing the performance of this type of algorithm is more challenging. And what you ideally want to have is some algorithms that we can have precise performance guarantees. Right, okay. So in this talk, I'm going to describe a very simple spectral method. There are a few people in the audience who have heard a version of this talk. I apologize for that. So there's this method is particularly simple, but it turns out to be quite versatile and effective in addressing some of the challenges that I mentioned. And what is this method? Okay, so we can consider first the rank 1 case. So yi is some unknown nonlinear function G applied to the scalar product, and Kasai and G are both unknown. And the method has 2 steps. First, you just form this matrix that is a weighted average of the scalar, the outer product of AI and AI transpose, and the yi's are the measurements. And the second step, you find the leading eigenvector of D, and that's it. Okay. So, and then it's a very simple method because it's easy to code. It's literally a one-line MATLAB code. Okay, just you run this and you get your estimate. And in the general rank R case, it's the same algorithm. What we do is, instead of finding the top eigenvector, what we can do is to find a few leading eigenvectors and a few trailing eigenvectors. There are specific rules for deciding R1, R2, and the summation is equal to R. Okay, so it's a very simple method. And personally, I first learned about this method in the paper by Natrabali and co-authors in the case of phase retrieval. They use a version of this method to initialize their gradient descent method algorithm to solve this non-convex problem. But this also appeared in earlier work, again, of Andreas in terms of matrix completion. But I want to mention that later I realized that this method is actually pretty old. It's a very old concept under the name of principal Hessian direction. So it's a paper in the early 1990s. And it's very interesting that in the title it says application of Stein's lemma. I will briefly mention why Stein's lemma appears in this case.
It's also in neuroscience.
I would imagine, yes. I would imagine that's the case, yes. Because I think one of the motivations for Lee to study this type of a method is to do a dimensionality reduction for these kind of exploratory data analysis and with applications in neuroscience. Okay, all right. So why does this method work? I'd like to start with a deterministic explanation without making any assumption on the underlying models for the sensing vectors AIs. And the way you can think about it is the following. Suppose you have a large number of AIs. These are n-dimensional vectors. The only assumption we need to make is that they expand, they point to all kinds of different directions in a sort of uniform way. Imagine that this is the initial distribution of these orientations, but when forming this matrix D, we are weighting different directions by yi, which captures the correlation between AI and Xi, the underlying true vector. So in a sense, we reweight these orientations according to the alignment with Xi. Okay, and then in some sense, the eigenvector D should feel this planted direction, right? Okay, this is of course a fairly rough type of explanation, but it is more robust than randomness assumption. We can say something more precisely if we make randomness assumptions. For example, in the case of a phase retrieval, if we assume the sensing vectors are ID Gaussian, just to begin with, and then if we look at the sensing data matrix, the data matrix is nothing but an empirical average of totally independent and analytically distributed random matrices. Okay, so every coordinate is independent, and then use a concentration measure of these random matrices. Then typically when M is large, this matrix should be close to the expectation, which we can compute. And this is the point where, in principle, you can use Stein's lemma, and you can see that in this particular example, the expectation is equal to identity plus 2 times the planted solution vector times Xi transpose. Okay, and I think in Lee's original paper, he used Stein's lemma, but if you use rotational invariance property of the Gaussian ensemble, is a much simpler derivation. Okay, you just shift Xi to the first coordinate, then it's a very straightforward calculation to get this. Okay, and the same idea applies not only to phase retrieval, it applies to other nonlinearities and also to the rank R case. Okay, and I want to just provide a remark that this idea does not work if the nonlinearity G is an odd function or an odd function plus a constant. In that case, you can see that this expectation has no gap. Okay, so there is no, this underlying constant in front of Xi transpose is 0 if G is an odd function. Okay, but in the case of an odd function, there are much simpler ways to get some correlation. All right, so the idea of a rank R case is similar. If you look at the expectation matrix, then you see that the majority of eigenvalues is equal to a constant. That's the bulk, but with a few spikes coming out that carries information, right? But of course, that's the regime where the number of samples is very large. When the number of samples is not large enough, for example, their proportional dimension, as we all know, that this bulk typically will expand. Instead of being a Dirac in the spectrum, it will expand. But if you have enough measurement, then they will not try to occupy these spikes. So these spikes can still be obtained, and corresponding eigenvectors carries information. All right. Okay. So the last perspective I want to mention is in terms of optimization landscapes. So again, we can use the phase retrieval as an example. This is going to be the optimization that we want to solve. We can think about it as the maximum likelihood or map estimation for solving the underlying Xi, and this is a non-convex problem. Now, the way to study the landscape of non-convex landscape optimization problems is to consider the Hessians, right? So we can compute the form of the Hessian of this loss function, and the Hessian has this very simple structure, and you can see that it is also of a form that you weight these vectors by these coefficients. Now, if you start, and this Hessian formula is evaluated at any given point x. If you set x equal to 0, or more generally, if you think about x as a generic point, because if you have a typical point, then the scalar product between x and a collection of Gaussians is very close, is very small. Then essentially, at a typical point, the Hessian has this form. This is exactly the negative version of the matrix that we consider. So in other words, this method can be understood as picking the direction that gives you the maximum descent, okay, in terms of a Hessian. Okay, so that's another explanation for why this is the case. And of course, you don't need to use this naive loss function. You can use a more advanced version of this loss function, and then it turns out you can have much better performance. And I will briefly come back to this point later on. Yes?
But your argument about A Gaussian,
Yes.
but that also shows the limitation where A is non-Gaussian. Then you get C, you get maybe subspace.
What do you mean by the subspace? I don't see. Yeah.
If you extend it to the case where A is not IAB,
Yes.
then you might still have the subspace spanned by the X's if you have other than individual C's. You may be able to recover the subspace spanned by the arc C's.
By the case, so you're talking about.
You have some correlation. You have C times some.
I agree with you. So even in the case, first of all, even in the case of Gaussian, you only recover a subspace. You don't recover the exact the magnitude, right? It's only the. But I'll come back to the point where you don't have a Gaussian. Okay, so.
With an application, that's all.
Yeah, because in, the Gaussian is a very special case of a larger family. Okay, all right. Okay, so. Performance analysis. This is a very simple method, but we want to understand its performance. The typical way to characterize performance is alignment between the target and the leading eigenvector. We can think about the angle, and there are a few earlier work analyzing the performance. Ideally, what they showed is that the angle between the true direction and the eigenvector can be made arbitrarily small with high probability if you have enough measurements, and this is a progression of results in the literature. Initially, what we need is m. The number of measurements is essentially n log n to the power of 3, and later on it's improved to n log n. And in the work by Yuxin Chen and Candace, they show that with some modification to the algorithm, you can make the sample complexity linear. And I want to just later I will point out exactly why initially there is an n log n factor, which you cannot really get away with if you don't do anything, if you don't do something to the measurement model. Okay, so here is on hindsight, it's a very simple type of proof strategy. What you want to do is you want to show by intuition this random matrix should be close to this expectation, which has this gap in the spectrum. And the first step is you use matrix concentration inequality to show that this is indeed the case if you have large number of measurements. And then because the expectation matrix has a spectrum gap, you can use Davis-Kahan perturbation theorem to show that the eigenvector of the empirical matrix should also be close to the ED. So that's the typical way to prove things. It's very straightforward recipe for proving all these kind of result. But from this analysis, you can also see that it's a bad idea to use yi as a weight. Okay, so why is it a bad idea? A very simple explanation, non-rigorous explanation to say that the yi's are not bounded. If you look at all these yi's, the yi's are nothing but the squared version of the inner product between a fixed vector and a collection of independent Gaussians. So essentially, the law of yi's are squared version of independent Gaussians, and the maximum value of yi, you have m of them, is of order 2 times log m. Okay, so that's the so it's not bounded. And then a very simple analysis of this eigenvector problem, you can show it's a deterministic result. You can show that the angle will converge to 0. The angle between the eigenvector and the true vector will converge to 0 if the maximum value of yi divided by the sampling ratio is going to infinity. So you can see that if the sampling ratio is finite, is order 1, but in this case, the maximum yi is 2 log m, then clearly the angle is 0. Okay, so that means if you don't do anything, the linear sample complexity is not possible for this method. And what is a fix? A very simple fix is just to do truncation. So instead of using the yi's, you say I throw away any measurements that are too large. Okay, it's a very simple idea, but it works pretty well. And then you can see that without this shrinkage or truncation, the performance spectral method gets worse if you increase the dimension n, okay, by fixing the sampling ratio. That means in this case, this is the indication that the performance is not in terms of linear sample complexity. But if you do the truncation, you can see that the performance stabilizes. So there's a indeed underlying limit. But since now, yes. Yes, that's the point of this slide. Since now we know that it's a good idea to do something to y before forming this matrix, we can formulate this as a problem of designing T, right? And in the literature, there are some proposals. For example, this is the original version, and there are different kind of versions. It all boils down to pick your favorite functional form based on your intuition, and then with some parameter, and you tune these parameters. And the general problem is what is the optimal form of T, okay? That can give you the best performance, right? This is the question that we can ask. All right. So, and also for this type of problem, typically there is a phase transition behavior. So this is just a simulation. The x-axis is the sampling ratio, and the y-axis shows all the eigenvalues, with the top line, the red line, being the top eigenvalue. And you can see that at a certain point, the top eigenvalue starts to separate from the bulk. Okay, this is I like this view because it gives you a dynamical view of seeing this problem, and it's also an interesting question to study this problem from the dynamics of increasing alpha. So this curve follows a deterministic evolution equation. Now, but anyhow, at this point there is a phase transition, and this phase transition eigenvalues also can be reflected in terms of phase transition in the correlations. So there is a critical sampling ratio where before that there's no correlation, so there's no information. But afterwards, as you increase alpha, then the correlation converges to 1. So in some sense, these previous work, what they study is the behavior of this curve when you are up here. When the sampling ratio is very large, the correlation close to 1. But what they miss is this this phase transition, or when you have not enough measurements. All right. Okay. So we can do some performance analysis by first of all, yes.
Can I ask you a question which is related to what I was doing before? This, I mean, the problem you're discussing is related to the fact that there is a Gaussian.
Yes.
If they were random variable at a norm, for example, on the sphere, then
yes, I will come to this point. Not fully answering your question, but a version of of your question. Yes.
You're talking about the problem of the yi unbounded.
yes.
It is not related to the bounded.
So he's talking about AIs. Your question was about the AI, the laws of AIs, right? Instead of being ID Gaussian, what about general laws of AIs? Yeah.
You said the one is not related to that?
But the boundedness of the AI is not related to the fact that the AI is unbounded is not related to the fact that the yi is unbounded.
Yes.
The AI can be bounded, but the yi can be
Large.
log n.
Yes, I agree with you. Yes, that's.
To the threshold that you were referring to, it has to do with this algorithm, or it is maximum likelihood?
Oh, okay. That's another point I want to cover. Yes, there are. We understand what is going on with the threshold, and also, okay. So for now, I would say that this threshold depends on the t, and also sampling ratio, the t, what type of the model that you use, and what is the linearity you use. But there is also a fundamental, a more fundamental threshold that you can say about this this problem. Okay, and then we do some asymptotic analysis. What we, I mean, for people doing random matrix theory, that should not be a surprise that there is this asymptotic limit for this angle between psi and x1, and there's also a phase transition behavior. And I also want to mention that initially when we did this work, we assume the measurements, the yi's are non-negative, okay, for technical reason. And again, Andrea and Marco, right? Yes, and they did a nice work relaxing that condition, so showing that yi does not need to be positive. Okay, there's also consequence of that. But the prediction is the same. So even that means if you even y is negative, you have the same formula. And I didn't write out exact form. Doesn't matter at this stage. But there are closed form formulas that you can calculate based on integration. That you can precisely calculate. And this is again a familiar picture if you're familiar with the spike model. What we showed is that if you have not enough measurements, meaning you're below the phase, then the angle is converged to pi/2, meaning there's no correlation, and the gap between the top two eigenvalues is also going to 0. That means if you are using power iterations, then you're going to see a very slow convergence. But things get much better if you have more measurements, and then there is a different phase. Then you start to have correlations, and there is a non-zero eigenvalues. Okay, and this might look very similar to this type of a spike model or BBP type of phase transition, but there's a little bit of a difference. So this model is slightly different from the classical spike correlation model. The classical so the model that we consider is A times diagonal matrix Y1 to Ym times this A transpose n times A. Okay, so and A is, for now we can assume they are the Gaussian random matrix, and Y is some scalars, some random variables. The classical spike covariance model considers a case where the laws of Yi has a bulk and some spike. Okay, and correspondingly after the action of these random matrices, you will see that depending on the sampling ratio and a few other factors, these spikes can survive these random matrices. But in this case, there's no spike in our model. The Yi's are the measurements. Okay, so there's no spike. But and also additionally, the Yi's depend on AI because the Yi's is equal to some function g of AI transpose times Kasai. So there is some additional correlations that you have to capture in this model, but it's not complicated. Once you know the exact way to handle this correlation, there's a way to convert this model to a parametrized form of the more classical model. Okay, all right. Okay, so this is about the characterization, and then we did some simple experiment. You can see that the lines, the blue and red lines, are the theoretical predictions, and these dots are actual simulation results. And the point I want to make with this figure is to show that although this is asymptotic result, it works actually pretty well even if you have a very small data set. Because 64 by 64 image, it's very small, but you can see that it's already predicting the actual performance very well. And similar generalization can be done if you have a rank R case. It's the same type of story, but you have to be more careful, and you have to solve a more complicated nonlinear set of equations. And in this case, what we study, instead of just a correlation, what we study is the correlation matrix between a set of eigenvectors and a set of fixed basis vectors. This is an R by R matrix. Knowing this matrix is proven to knowing the principal angle of the two subspaces. And then in that case, in the large n limit, they converge to some fixed matrix. To do that, you have to solve a R nonlinear fixed point equations. But for certain special cases, you can decouple these equations to make them effectively one-dimensional equations. All right, okay. Some simulation results. This is the model of multiplexed phase retrieval. So you have the measurement contains information about 3 underlying images, and the coefficients are also unknown. Okay, and then you can solve this using spectral method. You can see that this is the correlation that you would get. Right, and similar things can be done for a 2-layer neural network. In this case, we consider this model. Okay, we saw Lanka's paper, and then we tried this method algorithm on this model, and then we can see that the curves show the alignment between the corresponding eigenvectors and the corresponding, I think in this case should be size, okay? And as you increase the number of samples. And I want to say that the point of this spectral method typically is not to get the best possible result, but it can be a way to initialize your more advanced algorithms, okay? Suppose you have an estimation that has a correlation of 0.6. In a high-dimensional space, this is already a huge deal because a cone with correlation 0.6 is exponentially small in the space of spheres, right? So the rest should be simple. It's just gradient descent and so on, right? Okay, so I want to come back to the problem of how to design the preprocessing function. As I said, typically you can apply some function t before you form the matrix, and these are two examples in the literature, and indeed with some parameters. Indeed, you can see if you use different functions, you will have a different performance in the correlation, and even the threshold, the underlying threshold depend on the form and the parameter. So the question is, what is optimal t? And the question that we formulate is the following. Suppose we are given alpha, that means the number of samples per dimension. What is the corresponding t that can maximize the rho, the correlation? Okay, that's the problem. It's a functional optimization problem. You want to find the best function t that can maximize the correlation for any fixed alpha. And initially, I thought about doing this, but I thought about doing this in a numerical way because I was not expecting anything analytical. But then I read Andrea's paper. They showed a result that says that there is a threshold alpha, so-called alpha weak, and below that, what they showed is there's no choice of t that will give you a non-zero correlation. So that means that's pretty fundamental. But after that threshold, what they propose is a particular form of this function t that is positive. Okay, that's and for example, in the case of noises phase retrieval, this threshold in the real value case, the threshold is equal to 0.5, right? Okay, so there's a later on, I realized there are more fundamental reasons why there is this threshold. And in the case, so after seeing this, we thought about what is optimal t, because in Andrea's paper, this threshold, this form of function is positive, but it's not the optimal one. Okay, that's the maximum possible one. And then we did some further analysis, okay, knowing that it's possible to do some analytical work, and we found that this turned out to be the optimal functional form. That depends on the channel. Py given us is just the nonlinearity, the activation function, the channel. And then you use this and you can find this t star, okay? And then the way we found it was to use the asymptotic formula and pose it as an optimization problem. And then luckily there is a nice geometrical interpretation of this optimization problem in terms of finding a minimum norm solution in a affine space. And then there is a closed form formula that you can get. Okay, that's the form that we got. And then
what is S?
S is a Gaussian. In the case of real valued, S is one component of A, because it's a projection onto a vector, so essentially it's one Gaussian. And in the case of a real value case, S is a Gaussian. Otherwise, it's a rotation invariant complex Gaussian. Okay. So you can, in a sense, you can calculate all these. Okay. For example, this is one example. In the imaging cases, typically the noise model is given by Poisson random variables, and you calculate this using the formula that I showed you. This is the form, okay? But exact form doesn't really matter, but the point I want to make is to know this is the optimal function, you have to know the exact, you cannot do this by intuition, right? You have to know what is the optimal form, optimal formula, and then you can get this form. And then we will see that some simulation results, indeed, this optimal choice is indeed significantly better than a heuristic choice in the literature. Okay, it's also a little bit better than the work in Marco's and Andrea's paper, we achieve the same threshold by definition, but afterwards, this choice is better. And I want to say that you get better result without increasing computational complexity because it's essentially the same algorithm, just use a different function t. So you should use this form.
So it doesn't depend on alpha.
Excellent point. So yeah, I should have mentioned that it's a little bit surprise to me that this optimal t star does not depend on alpha. It's uniformly optimal over all alpha. Okay. So, I mean, you don't need to know alpha, but of course you always know alpha. So that's. And then there is also an interesting observation that this type of a threshold, correspondingly, there is a fundamental threshold initially derived in Andrea's paper, but also it's also achieved by this type of optimal preprocessing function, correspond to the computational threshold obtained by using, for example, approximate message passing algorithms. Okay, so there must be a reason, underlying reason why this is the case. It turns out this optimal function t has to do with the Hessian of a loss function that is the loss function that AMPE or other type of message passing algorithm is trying to minimize. Okay, and that's also the fundamental reason that below that you cannot do much using a computationally efficient algorithm. Okay, right. So this is what I want to just say. All right, and then some additional simulation. This same type of optimal preprocessing can be applied to the multi-rank case, but you have to do something more special. It's a little bit more complicated. Depending on different subspace, you have to apply different optimal function to achieve the best performance. But you can see that this is the comparison between a heuristic choice versus an optimal choice. The higher the better. So we can see that there is indeed a big potential improvement that you can gain. All right, so I want to come back to the point where the sensing models are not Gaussian. Okay, so this is to practitioners, this is just a pure theory, right? You use Gaussian, but practitioners are dealing with matrices that are more with a stronger correlation and more general structures. So here is just a recap. So in the case of a phase retrieval, what we are assuming is so far is that A's are ID Gaussian random variables, or you can make it a sub-Gaussian, but these are far from the reality of imaging, right? So one specific actual imaging setup that we can consider is so-called the structured sensing, or the so-called coded diffraction pattern type of measurement model. So here, the sample is a Kasai. You want to estimate an image of this sample, Kasai vector. And this is the sensing setup where we place a pseudo-random mask, a phase mask, in front of a sample before taking a phaseless measurement. Okay, and then you can do this experiment multiple times by changing the mask. But otherwise, the sensing setup is the same. Now, that means you just use a different diffraction pattern and so on. So mathematically, what we're doing is every mask is equivalent to multiplying Kasai element-wise by a pseudo-random pattern, followed by Fourier transform, because that's the actual optical imaging, and then you take you lose the phase, right? Right. Now, if we discretize the model, then a sensing matrix A in this case has a particular structured definition. So in this case, A can be written as a block matrix where each block is equal to a DFT matrix times a random diagonal matrix. And the random diagonal entries correspond to the phase shifts on the pattern that you apply. For example, you assume diagonal entries are randomly drawn from plus minus 1, plus minus I. Okay, so this is the case, and there are indeed some analysis of this type of model, but as you know, it's much more challenging to analyze than a Gaussian case, simply because there's not enough randomness that you can directly apply. So there's a paper by Candace, Lee, and Sultan Kotabi. And then what they showed is that the number of measurements must be greater than C times N times log N to the power 4. So there is additional log N factor coming back. Now, the log N to the power 4 might look very innocent, but if we do a back of envelope calculation, N is the number of pixels, is 10 to the power 6. Log N to the power 4 is a much larger number. So essentially, this theorem, this type of prediction is very pessimistic or very, very conservative. They're saying that we need to take that many oversampling factor to guarantee the performance. But the actual performance of this type of sensing ensemble is much better. So what we showed here, the red circles are the performance of these structured sensing matrices as a function of the sampling ratio. You can see that even at 6 times oversampling, the correlation is already very, is close to 0.775, but they are different from the Gaussian ensemble. Of course, because this is a different ensemble. So what can we do about it? Clearly, if you run experiment, there is a concentration behavior. You can see there is an underlying limit, but what we can do about it? The way we do it about it is to exploit, without proving, but exploit universality. So you can see that CDP is one particular ensemble of matrices, but we can test 2 additional ensembles. One is so-called random frame ensemble. What we do is you start with a dense unitary matrix, okay, for example, the DCT matrix, and then you randomly subsample the columns to form the same aspect ratio as the CDP. The third ensemble is unitary, so you form a random Haar matrix, and then you pick the first n columns, okay? And you do experiment. You will see that they follow the same curve. So of course, this is an indication of universality behavior, and I want to mention this type of universality has been observed in other systems. It's, for example, in compressed sensing and so on. So, and we also did some more careful experiment as a function of n. We can see that they all essentially follow the same curve. And initially, last year, what we did was to analyze this problem based on subsampled Haar matrix, because that's the ensemble that is still very close to the Gaussian ensemble because of rotational symmetry and because of availability of tools. So initially, what we did was to use the replica method to calculate the asymptotic limit of this angle, and then we got some formulas, and there are exact formulas for these limiting angle and the threshold. And then one technical step, if you're an expert in this, you will know that one technical step is to calculate a version of the HCIZ integral. But then here is some simulation. We can see the blue line is the replica prediction matches exactly with all these ensembles, okay, including the CDP. So that means from that, we know, of course, that's not a proof, mathematical proof, but from that we know we have a formula to predict the CDP. But what is nice about this formula is then we can start thinking about what is optimal optimal preprocessing function that we can use for these kind of a CDP. And I want to mention that we did a replica method, and early this year there is a paper from Arian Malaki's group. Arian and his students rigorously proved this prediction using an application of free probability theory. Okay, so it's not, yeah. All right. Yes, okay. I'm almost done. Okay, that's perfect timing. So, yeah. Okay, so as a summary, what I described is a very, very simple spectral method. It's a one-line MATLAB code for estimating a low-rank subspace from nonlinear measurements. And the motivation is, there are multiple motivations. The way I first got interested in this method is in terms of initializing optimization algorithm for non-convex optimization, because the spectral method can be a first step, right, to get some correlated guess, and then you do follow up with random initialization. But there are other applications such as the nonlinear dimensional reduction. It's a very old idea I want to mention. Okay, and there are, if you make assumptions about the sensing ensembles, you can have a precise high-dimensional characterization. There are phase transitions, and what I particularly like is the implication of having knowledge about this asymptotic prediction is that you can start doing optimal designs, and from the optimal design you can get better performance in terms of correlation. All right. Thank you for your attention.